So hello everyone, welcome to the PSCAD Advanced Code Day 7 lecture. So our lecture number 6 basically, that is day 7 on the second part of solar model. So in the previous lecture we have covered the generic solar farm. So now we are basically implementing the complete solar farm. So in order to understand the solar farm modeling in PSCAD, so first we understand the PV array model that is given in PSCAD. So let's open this PSCAD file first. So this file will be open in PSCAD, so which involve different components. So mean there is no extra components, like you can say the user defined components. Already these components are available in PSCAD. So you can see that there are different components including irradiation, temperature, and then the rates, basically to change the irradiance and temperature, and then the PV array, and more important, so you can see that there is a variable resistance that is connected between the terminal. So that resistance is controlled through this circuit, so which is, you can say, the simulation time dependent resistance. So it means that we will, once we resistance will increase over a mega ohm within a second. So mean if there is a change in time, a very little change, and it will give you a very large change in resistance, so that you can get the maximum voltage across this PV array. So here you can see that there are two inputs to this PV array. The first input is the basically irradiance, that is solar irradiance, and next one is a temperature, and which could be varied through this slide bar, and the controls are given here. Like if you see that, if we double click on this control slider, so here you can see that the maximum value of temperature is given 55 degree, a unit is also given, and the minimum value is 0, but the initial value that it will take, that is 28 degrees centigrade. And similarly, the irradiance, that is watts per meter square, is given, and initial value is 1000, and which is also a standard you can say irradiance at standard temperature condition, that mostly taken as 1000 watts per meter square, and minimum value is 0, and the maximum value that goes to up to 1500. So but it depend upon the effective hours of mean the location as well. But up till in this simulation we can say that we are using the standard value, that is 1000 watts per meter square. So here you can see that, so after this there is a, you can say, rate limiting block is also connected to both inputs. So it means that if there are parameter, basically these are blocks are added to avoid any errors if the quantities are abruptly changed during a simulation. So in order to avoid any error in the simulation, so we have added this basically rate limiting circuit as well. So next important thing is that PV array and its parameters. So when you double click on this, so here you can see that in PV array there are different modules that are connected in series, and overall it consists of, you can say, 130 modules strings in parallel, where each string has a 35 modules. So mean here you can say, and also for one cell, that there are, you can say, a number of cells connected in per module is 35. So this is the information of your, you can say, PV array, and also PV cell parameters if you select. So these are the basically effective area per cell, and the series, these are the manufacturer details for the, if you are using the Longi solar or you are using TNS solar. So depending upon the manufacturer, so this data, that short circuit current, like saturation current, and the temperature, and the diode ADLT gap factor, that we have discussed in the previous lecture in the MPPT diagram. So mean that in the voltage and current characteristic. So these are the basically parameters to that are used in the MPPT. And next thing is that the monitoring, mean which parameters are monitoring, because we are just introducing this circuit. So definitely this circuit will be the part of our main solar farm, so we will see this will also. So here you can see that the MPPT will take two inputs. So the one is the voltage of the array across the array, and the next is the current through this, the output current of the array. So in MPPT circuits, so we need to provide the short circuit current and the open circuit voltage. So here you can see that the open circuit voltage is given through string. So it means the VOC. So VOC is given through the label value. So it means the VOC is 1.015 per unit. So that is given here exactly. So similarly, the initial value of VMPP, that the maximum voltage is 1 kV, and tracking algorithm. So there are two different algorithm: incremental conductance based and perturb based. So we are using this one algorithm, as this is by default algorithm as well. Okay. And next thing is that there are two plots that are available here. You can see the XY plots. So one is V on the X coordinate, and the next the P is the basically the real power across this, and similarly the V on the of the PV and IV on this character. So these characters are similarly you can expect the like here in the PPT curves. So the maximum point will across this where the voltage and VO max and I short circuit current. So in order to run this case, so click on the run button. So in the simulation box, so simulation has been started. So here you can see that these are the two curves that we have obtained: the maximum the voltage across P across voltage, and the maximum VP. So here so these two curves are generated from this, the characteristic that are mentioned in MPPT and the PV cell parameters. So this is how basically we can measure. So this is just simple component that is modeled as a PV array. But if we unload this one, and we know, and then if we open the same case with the complete solar farm. So here you can see that that's very important. The complete solar farm is here from left to right. You can see that there is a solar farm that is connected at POC 33 kV voltage level, and through a pi transmission section it is connected to the grid. And then there is a fault logic, like fault type is available, that depending on the dial, I mean we can select the which type of fault we need to apply. And next important thing is the power plant controller here. So I mean that power plant controller perform three function, that basically two, that will control the real power and reactive power, and that will supply to the solar farm to maintain the solar farm you can say behavior under transients as well as under steady state. So one by one we will start exploring these components. So let's start with our first power plant controller. So in power plant controller you can see that there are different inputs, and there are different reference value, and there is a different output. So at this point the first component is that the delay block. So it means delay block is that the power plant controller will be in action right after once this solar started, and like MPPT is in function and solar reached to its maximum steady state value. So here you can see that when you click on this, so here you can threshold value is 0.2. So it means that this PPC will be in action right after 200 milliseconds. So it means that 0.2 seconds. So it means after 200 milliseconds, like after simulation, PPC will be in action to control the point, like the voltage grid P, Q, and V at the point of interconnection. So okay, this is delay block is given to here this PPC, like power plant controller. So here you can see that there are three inputs: the VRMS POC, and real power POC, and the Q POC, because it measures some values from the grid, and it will do a comparison with reference values, and it will generate P and Q based on the algorithm developed in PPC. So right now we are not discussing the algorithm. I will show you, but up till now you can see that there are three inputs. Mean for that, in order to model your PPC, you must have three inputs. Now here these are three inputs. When you click on this ammeter multimeter, so here you can see that you have selected measurements, yes, active power, reactive power, and this RMS voltage. And here you can go through signal name. So here you can see these are the signal names. So I mean VRMS POC, PPOC, and QPOC. So these three elements, like three measurements, are being added, like you can say the measured values are feeding here. So these are taken as the input values up to PPC. And similarly, there are different reference values for PPC. Like here and for V reference, so because as per the contingency criteria under n minus 1, so we should have a maximum voltage of plus minus 10%, plus 10%, and minus 10%, like 0.9 and 1.1. So this is our range. And similarly for P reference, because here you can see that the number of units in this solar farm is 100 and the E turbine have a rating of 0.25. So we will see, I mean, in the solar farm, so these are added. So you can see that this is basically, that will become 25 megawatt. So therefore it is a P reference value of maximum 25 megawatt and minimum is 0, because P solar has a no capacity like synchronous machine, so it has a 0 or 25 value. So there is no either negative side here. So therefore only this range is given. And similarly the Q reactive, that is depending upon the value and the power factor as well. So mean 1.0 power factor is given, like 1 unity power factor. So these are basically inputs. These are the starting point of PPC, and the next point is the reference values. Okay, this is the first initial point, information regarding the PPC. Now next important thing about the PPC is that is the PPC parameters. So for that, right click on this and added parameters. So when you say added parameters, so there are different things that are added here, like power plant ratings. So number of inverters, I mean either you can give through string or you can directly write it here, that is 100. So I have said UN. So I mean inverters are given here UN. So UN is through label. It means that its value is 100. So because ultimately it will goes to here. And similarly, the MVA rating of single inverters, that is written in the format of string, that is rated megawatt. So rated megawatt is here. So that is given as a 0.25. So again 100 multiplied by 0.25, that is 25 megawatt. So where we have taken this value? Exactly from the array, that initially we have the array model. So if you are working on this solar farm, you don't need to model the array. You directly give this number of strings and the rated for each turbine, like each power, each inverter, each string, then you can multiply this. And similarly the control parameter, so right now there are different controls associated with that. I mean this power plant controller has three functions. Either it has ability to control POC voltage, either it has ability to control power factor, and also it works at a fixed reactive power. So therefore, because of fixed reactive power, so we have not given any Q reference to this, like Q reference is 0, because it's not changing with respect to any reference. Whatever the value, it will give you the fixed reactive power. So because so if in solar inverter has some capability to provide reactive power, that will be enough. So I mean depending upon the power factor, it will not change. And similarly the operational limits, I already told you that either it will give you the 25 megawatt, that is 1 per unit, either it will be 0. And similarly based on this Q max power factor working, that is has a capacity to give 0.6 Q max and minus 0.6 Q min. And similarly that is a voltage right through detection, that is 1.15 and 0.85. I mean whenever the voltage goes below this 0.85, there will be a LVRT detection will be in action, and then it will clip the voltage, and it will, you can see that it maintain, power plant controller will maintain the voltage above the 0.85 and below the 1.15. So high voltage right through and low voltage right through. So we will see how this circuit basically if acting on this PPC. So now one thing is clear here. I mean we have a power plant controller that has a ability to control uh, real power like the voltage as well as the power factor. And here you can see that the POC voltage, power factor, and the fixed Q. So it means it has capability to give three control. But some based on the manufacturer like SMA and Tesla, they are including different other control as well, like the frequency control as well, and the variable Q. So right now this is you can say the generic solar form. So therefore the purpose is to basically understand that what are the key parameters for the plant power plant controller, and what are the key outputs to this solar farm. Okay, next thing is that in order to see the definition of PPC, that's very important. So for that, double click on this. So when you double click on this, so mean the complete circuit behind this block will be open. So here you can see that the first thing is that you are converting your S base to the inverted S rate. Why? Because you need a division, you need a per unit values. So every time you need to something divide by the S rate, inverted S rate. So you have calculated inverted S rate here. So through S rate, after S rate, yeah, here you can say V reference is already is a base value that is taken as a per unit, and P reference that is P per unit, and that is Q reference that is Q here. So here you can see that the P Meyer value is multiplied by the inverted S rate, that will give you the per unit value. So mean from this actual value you are getting the per unit value. And similarly, if you need to get a Q value over the P reference, then you need to multiply it by A tan theta. So mean you can see that the P tan theta multiplied, you will get the Q values. So this is basically the same formula is here. So these are just few calculations so to get into the power plant controller side. Okay, next important thing is that the you can say that generate POC reference for plant. So again, if I go back to the simple main plant, so here I mean I need some reference value. So these are the reference values that are created at here. So mean here you can see that there are 4 PI controllers are available. So for each gain, there are in order to adjust the gain, the slide controller bar is added here. So mean you can simply slide this controller that is available in your like control component bus in the master library, and you can change these gains to adjust the gain, and so that you can get the actual like the value close to your measured value. So here you can see that your measured value in per unit. So where you have taken the same value here, the measured value, and then you convert it into per unit, and that will be here. So means this is a single worksheet. You have added different circuit, and you have taken a difference from reference value, and then added the algorithm for you can say PI. That is we have already discussed in previous lecture how. So in order to basically the purpose is here as a planning engineer. If we do all this work as a designing engineer, then we must know all the parameters behind this controller as well. So our purpose is to basically test this solar form against different fault to see that whether this power plant controller is working or not. So therefore, so we are not interested in the PI functions inside this. So otherwise there are a lot of things here. I mean, everything that again the PI block that I explained in the previous lecture as well. So mean we need to see that, mean we need to adjust this KP gain for that to maintain that we have the settled value after the some time. So therefore coming back to this reference value, so we have generated P reference here. So again, because the voltage reactive power has a issue with this voltage as well. So in order to calculate the voltage and from the Q, so here you can say the first is V per unit and then V per reference, and we get this one value. And similarly the Q ref the measured value, and then we will taking this Q measured value. So where we can see that is Q over P. This is the same thing, that is basically we have generated that is measured value. So we have taken the difference, and then this is another input, and also then Q measured and the Q reference value, that is another output. So basic depending upon this dynamic data tab, so mean we can select mean up to which, so we are merging our value, that is Q per unit. So it means the power plant controller has only two inputs, the P per unit and Q per unit. So same thing will be back here, the same thing is given basically feeding these two outputs to the solar farm. Now these inputs, these two output of power plant controller will become the input to the inverter. So before going to show this, so just go to see the added parameters for the solar our simple solar form. Here again un number of inverter, the system frequency base that is given in term of F base, that you can see here, that is F base is given here, that is 60 Hz, and similarly V base is taken as a 33 kV for the solar form. So therefore, so this is the way to basically show your data. So sometime you for example, for manufacturer model, you can't see this type of information. That only the mean the some informations are available and some are encrypted inside the Fortran code. So therefore, so that depending upon the type of like you can say the modeling that you are doing. So here similar, the V base is also through string, and the base inverter voltage, that is 0.6 kV, and the base DC voltage around 1 kV, and the base leakage inductance has 0.2, and then limits that we have added same things that we given in the power plant controller as well. And the ramp rates for the real power and reactor, mostly that by default we add 1 per unit second, mean it takes to the peak value using this ramp. So this is how basically you can see that these are the solar parameters. So next important thing again is the solar farm block. So here you can see that there are different things that are associated with that, starting from this main circuit. So in the solar farm, there same thing, this is a PV array. So I will highlight some few things here that are important. The first thing is the PV array. So input output of this PV array will be IPV and VPV. Definitely it will give you two inputs, and these two outputs considered as an input to the boost converter. So when these two inputs are given to the boost converter, so what is the purpose of boost converter? So it's basically increasing stepping up the DC voltage from one voltage to another voltage, so that it will give you IDC and VDC. So mean the current through the boost converter and the voltage across the boost converter. So same, the current and this boost converter output taken as an input to the inverter. So these inverters will perform its duty to convert into AC. And in order to basically damp and mitigate the harmonics, we have added the LCL filter and damper circuit to basically save, and then it is connected to the grid, and then this to basically adjust the taps, and then it you can see go back to this point like in the main circuit. So this is the same point. So this is how basically you get the overall view of the circuit. So mean now important thing is that what are the control involved with this. So first control involved with this irradiance and temperature, that is you control through this slider form. And next important thing is that you must have a G boost. We need to generate this duty to basically control the switching of our converter to get maximum voltage, to get a step up voltage. Okay, next important thing, where are the control involved? These are the switching pulses. So I need these 6 switching pulses with 180-degree conduction and 120-degree conduction, depending upon the like you can say switching techniques that we are using. So therefore, now important thing, if we know this value, like what is the gain and what is the pulse value, so that's simple. But if we don't know, then we must know the structure, I mean how to generate these pulses for this, for the boost converter, and similarly for this these 6 pulses. So if you are working as a planning engineer, don't worry about that. Mean everything will be given by the manufacturer. Just you, what you need to do is to basically test your plant as per your planning code. So I will show you in the practical project in this after this lecture. So this is but you make sure that you must know the process, mean where extra circuits are needed and where some protections are needed. So mean I have told you, mean 6 pulses for inverter and 1 pulse for G boost, like the converter I have required. Okay, one by one I can show you something. So these are the same thing, the KPI gains for the all the PI controller, that is for the inverter control parameter. So mean in order to generate these 6 pulses, so from the start, so mean we have imported parameter from the base case, like from the first main parameter. So these all through you can say in the component tab through export, you have added this all these things and you have exported to the main at this page. Okay, that's okay. And then you can see that again you have a delay block you have created, and same thing you have inverted S rate and inverted S base to get the per unit values, and also and some right after you can see that this is the per unit calculations for the P from the DQ to from you can say DQ transformation. So this is a complete basic theory that involved in the design of solar farm. So in order to get more information, you can basically do a literature review for this each parameter like inverter, inner current controller. So the main purpose is that we must know, mean we should have these values like the firing pulses that we are generated. Ultimately what we need, these are the basically 6 pulses here. So I can show you one thing. Yes, here. So this is the first pulse, G1, G4, G3, G6 and G2 and G5. So these 6 pulses are given based on the firing, the PWM technique, and that are given here the same thing like here G1, G2. So based on this, this is working, mean that the inverter performance will be in action, then inverter will perform its duty to invert the power. And similarly here, in order to control the boost converter controller, so the previous one for the inverter controller, in boost controller the same thing is happening that we have done in the previous lecture, that we have get the VDC like the output of our you can say the this our main taken as a reference of the converter. And similarly all the MPPT inputs that are passed through the PI controller and given to the reference boost, and we get this G boost. So this G boost is a pulse that is taken as a input, basic control input to this boost converter. So here you can see that there are 5 pulses, a total 7 pulses. 6 pulses are here that are basically complementary pulses, mean if one in one phase, 3 phase and 3 on other phase. And next this another this G boost to mean the complete circuit that we have done this all efforts only to get these 6 pulses and 1 pulses. So that is the switching mechanism, mean how to basically operate. Otherwise solar farm has this only these components, mean the PV array, then boost converter, and right after the voltage source converter, and then basically it inverted the power, then GSU transformer, and you get the P value. So this is how basically control the main circuit. So the important thing that we will understand, mean mostly say the dynamic studies of solar plant. So dynamic studies of solar plant means that it's not about the modeling of all your design components, it's about the testing of your components. So mean all the manuals, all the data sheets from the manufacturer will be provided to you, and even the model and libraries will be provided to you. You need to test this plant as per the planning code, that is through LVRT, HVRT and different fault type. Like here under fault type you can see that there are different fault types are given, mean you can select the fault type. So based on this, mean where we can get here in the fault type, the you have added the control through external. So when you click this fault logic, so mean you are applying the fault for a 5 second, and the duration of fault is this. So mean you can change this fault time, fault cycle, and you can apply the fault situation. Okay, and similarly, so based on this, so mean the fault that we have performed, so we have added this fault type here. So mean because this is not a mean internal, these all these components for internal. So in the configuration we have added the only the external block. Okay, so right now if we say that, mean the complete solar farm is connected with this POC at 33 kV voltage level. So here you can see that we can see the slider button that the fault logic is applied at here. Now our important point is that, mean we have a dial switch from 0 to 11. So mean from 0 to 11, so there are different faults position that available that we can select. Mean from 0 to 11, mean for different fault different is given. So for that, now mean how to basically add this fault. So mean for dial button, like here if we double click and press on help, so here you can see that the different parameters are given like in the configuration. So here if you right click and say help, yeah, so for control panel, so mean variable input slider that are given, and that basically make you the select how to fault the select the type of fault in the solar plant. Okay, so up till now mean the complete solar farm is modeled. So under this home section, and first is to basically build your circuit, and you can see is there any error or not. Okay, run is completed, it means there is no mean modeling error, so run your case. Because it's a larger network, so it will take some time, but it is basically important to have a you can say interval Fortran in the dependency section. If you go to system options and then here in dependency, sorry, in here you must have checked this version to interval Fortran, otherwise using G Fortran it will take a lot of time. The next important thing during this simulation, so I want to show you that here in this section, like we have seen that under this PSCAD, when we right click and help, so there are different, when we say there are 11 fault that are option available, like if I say a code is added 0, then it means no fault, and if code is added 1, it means phase to a ground fault. So that is basically controlled through the dial switch, which code is has given to this, so that is given is here. So the dial position for this is 2, okay, and number of dial position is 3 to 10, so it means under 2 section, so it means the phase B to ground, so phase B has a fault, so only we are accessing a single line to ground fault here, so depending upon this fault we can perform. So now again simulation is started. It's taking time because it's a you can say that complete circuit. It's basically solving all the equations as per model, so therefore it's taking some time. Moreover, also you can see, you can change the project. Under the project you can do change the time setting as well, to basically under runtime solution type steps you can add 50 to basically add also you can reduce this to 10 second, why you are running for 20 just for say 10 second. So around 8 and 9 seconds case is running, so here you can see that the summary, the 46% complete. Okay, we can stop this simulation here. And also next important thing is that under the graph section we can see the values, like we can see that the voltage is around nearly 1 per unit and the maximum megawatt. In order to get the voltage in the range, just select and press R and press R, so it will automatically range your graph. So here you can see that the voltage rised up to 1 second, and right after, as per the given time in the fault block section, so we can see that the fault time to apply at 5th second the fault is applied, and the fault for this is 0.11667 seconds. So in order to calculate your cycle, you can multiply with the frequency. So at 5th second, you applied fault, then cleared, and then it's back. So because it's a single line to ground fault, therefore voltage is not reduced to 0 at the POC. And similarly, the megawatt and megawatt. So megawatt and megawatts have the opposite response, but the megawatt range up to 25. And also you can see more simulations as well, but if you need in the range you can also see that. That's a V grid POC in kV, that was in per unit voltage, and also the I grid, that is current, that is given to the grid value. So for the planning perspective, you need to see this much violation, either voltage are within range, under the fault, either all these things are okay. So this is how basically you test. So dynamic study, so for if the voltage okay, so it means that the things are working fine. And similarly the real power and reactive power. But in order to test the internal function, like inside the solar farm, we have seen that there are multiple graph added. So these are for the, you can say, for the design values. If you are working as a designer, you need to see the behavior of solar plant, then you measure these things. Otherwise, as a planning engineer, we are interested only the key parameter that are associated with the planning code. So as per the planning code, like as mentioned in the power plant controller, that an added parameter, we are interested in this voltage and power factor and the Q, most important. And sometime if frequency control is enabled, that is also part of this simulation study. So okay, this is basically the solar farm is now first, the part 1 and part 2 is completed based on the theoretical background. Now in the next lecture we will directly run our case for the manufacturer model, and then how we will see how we perform the dynamic studies for that part as well. Okay, thank you.